All right, so chapter 4 is all about identifying scientific variables. This is the last chapter that will be part of exam 1. So when you look for ways to identify the criteria as well as measuring the variables, you want to make sure that you're meeting both of these. You want to make sure that it's observable and that it's a replicable variable. You have to explain how the variable was measured. That's the observable part. And then you want to describe under what conditions the variable was measured. We do that so that other researchers can recreate the same conditions to measure the same variable that you did, which is the replicable side. If we were going to conduct a study such as this one, this is something that we could replicate across multiple groups of participants. So if we have them read some kind of short paragraph that has colored font, or some of the font is colored or keywords are colored, and then we had the other group read just plain, typical black font, we would be able to use an eye tracking device to measure how quickly they read, how long their eyes are focused on certain words. So maybe they're drawn to the color words. Perhaps they're reading through the colored words faster. But we can measure the amount of time down to milliseconds to try and get a sense of, are they reading more quickly and efficiently when they're seeing colored words versus the group that is just given the black font or plain words. So we would want to test this among multiple groups to try and get that, reliability, and the test and retest reliability is what we would be looking for. When we go to examine constructs and operational definitions and things, it can be challenging to try and define certain things or certain terms. So we take a look at, what it is that we need for a good research study, right? We need a good sample size, we need a representative sample, we need a sound methodology. So if we were going to define happiness, how could we do that, right? How would we define happiness? And, it doesn't matter what answer you come up with. There's no single way to measure happiness. And so we can come up with various ways to measure it. Such things as happiness, which cannot be directly measured, is what is formally called as constructs. There isn't just one way to measure things, such as memory, happiness, guilt, intelligence, effort, age, hunger, even something like itchiness. We can't come up with one way to measure them. So, these are all constructs of, trying to come up with a more formal definition, and then we can come up with a way to try and measure them. Something like measuring intelligence. You could take an IQ test, or you could look at grades. If you're looking at age, you could look at maturity, you could look at, age in years, you could look at wisdom. Something like hunger, we could measure through how often your stomach growls, how deficient your body is in nutrients. Those are ways in which we can measure hunger. So these are all constructs of these ideas. So we try and come up with some kind of operational definition to better explore these constructs that we have. So something like depression, if we want to study that, we could use the score on Beck's depression inventory. Right? So that would be our, operational definition to use that. If we're going to look at hunger, we score, or we identify what the amount of food that's consumed through grams, by measuring grams. Stress, we look at the levels of cortisol, or the stress hormone. Anger, we're going to look at the number of profanities uttered per minute. Happiness, the ratio of minutes spent smiling to minutes not smiling. Health could be your resting heart rate. Obesity could be your body mass index. Effort could be the minutes you spend studying for this exam or any exam. Brand loyalty could be number of products purchased per year from a particular brand. All of these are operational definitions so that other researchers can understand what it is that we're studying. These just go through some other ones that were listed in your book, apart from the examples that I just gave you, which were not in your book. So you can see the variable here is attraction, anxiety, and recall. And then we have different operational definitions that are written to try and measure, how we see attraction, how we try and understand anxiety, as well as how we try and understand recall, which would relate back to a type of memory. So as you read through this slide, you can see, trying to define something as age is not as simple as we might think. It depends on what the researcher is focusing on. So, they talk about in this example how the researcher wants to examine age and be very precise. So maybe we're looking at, somebody that's 25, 25 years, 3 months, and 6 days old, versus another researcher might just say, okay, they're 25. But that makes a difference in terms of how they set up the experiment, what it is that they're looking for, and how they analyze the data that, that were done once they're done. And then, how do we measure addiction? Are we looking at how many times they drink in a week, in a day, how many years they've been drinking? That's like a whole nother side to trying to come up with a way to define what it is that we see as addiction. So the precision that we need when we set up an experiment makes a difference in terms of other researchers being able to replicate the research that we do down the line. So that's why we need to be very clear in our operational definitions when we write them. A little different than what I suggested on the last page when measuring addiction. Their researchers here aren't even looking at how much the person drinks, but they're focused more on the withdrawal and the, trying to stop the drinking. And so here they're suggesting that we base whether or not a person's an addict on what the criteria is for the DSM-5. So that's a complete different setup to the experiment than what I suggested on the last slide of them, measuring whether or not they're an addict based on the number of drinks that they consume. So, this outcome that we get, or the results that we would get from the study I suggested on the last slide to this slide, could be completely different and in terms of what we find in our results. So we would need to operationally define both age as well as what we mean by addiction for a study like this. So looking at continuous and discrete variables, if you were going to take an introduction to statistics class, this would be one of the first things that you would learn is the difference between these two. And discrete is something that you can count. You can count the change in your pocket, money in your bank, money in everybody else's bank account. It might take you a long time to count everybody else's bank account, but the point is that you can count it, right? The continuous is just kind of ongoing, right? Something that can constantly changes. So, if we were going to go up to a pond and count the ducks in a pond, that would be discrete because we can look at the pond and identify how many are there. If we looked at the height of a student from age 5 to 15, that would be continuous because height varies, right? It's going to continuously change from age 5 to 15. It's not constant for 10 years. The number of animals in a zoo would be continuous data because the number of animals varies yearly depending on the reproduction of new animals as well as the arrival of new animals. If we look at the result of rolling a dice, that would be discrete. The result of rolling of dice is 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth, however many are on that die. So you're going to get a specific number. The number of books on a rack would be discrete data. It's something that you can continuously count. Age would be, well, age would be continuous to start, because you would have to, if you're going to look at somebody's age, you would say they're 25 years, 9 months, 5 days, 7 seconds, and then you go down to milliseconds, nanoseconds, picoseconds, and it just goes on and on. So you'd have to change that to discrete by saying, I'm measuring age in years, or I'm measuring age in months. The number of planets around the sun, that's discrete. The number of stars in the space, that would be continuous. Right, those are examples of both types. Quantitative versus qualitative. Quantitative is going to be your numbers based, so number of students in a class, number of square feet in a house, population size of a city, age of an individual, height of an individual, versus the qualitative variables are sometimes what we refer to as categorical. We can put labels or names and fit them into categories. So eye color, gender, the breed of a dog, the level of education, marital status, things like that would be considered qualitative type data or variables. This just offers you a few more examples of discrete versus continuous variables. And some of these I mentioned on the last slide, but you can read through a couple more examples. Some other types of variables we look at would be binary, nominal, as well as ordinal. Binary data is discrete data. It can only be separated into 2 categories, yes or no. You could choose 1 or 0, off or on. Sometimes binary can be thought of as a special case of ordinal, nominal, count, or interval data. Binary data is very common outcome variable in machine learning classification problems. For example, if we wanted to create a supervised learning model to predict what a tumor, or whether a tumor is malignant or benign, right? That would be considered binary data. Excuse me. Nominal data is made of discrete values but has no numerical relationship between the different categories. Like the mean and the median are meaningless. Animal species is one example. For example, a pig is not higher than a bird and lower than a fish. Nationality is another example of nominal data. There's just a group membership, but there's no numeric order to it, right? Being French or Mexican or Japanese does not in itself imply an ordered relationship. All right, so there's no classification to order from a numbered standpoint. Ordinal data is discrete integers that can be ranked or sorted. And so a defining characteristic is that the distance between any 2 numbers is not known. For example, the distance between first and second may not be the same as the distance between second and third. If you think about like a 10K race, the winner might have 30 minutes. The second place might have run 30 minutes and 1 second, but the third place runner might have gone 40 minutes. Without the time data, we don't know the relative distance between the ranks. We only know the order that they placed. So here's some examples of confounding, latent, and composite variables. And I want to give you a few other examples too, besides the ones you read here. So if you look at a confounding variable, it's one you didn't account for. You can disguise it with another variable's effects. So confounding variables can invalidate your experiment results by making them biased, or sometimes suggesting a relationship between variables exists when it doesn't. For example, if we're going to study the relationship between exercise level, which would be our independent variable, and body mass index, which would be the dependent variable, but yet we don't consider the age of the person and the effect on these factors, this becomes a confounding variable and it can change your results. The latent variable is one that we typically use just in social sciences, but it's a variable that's inferred using models from observed data. For example, in psych, we like the latent variable of generalized intelligence is inferred from answers in an IQ test. That's the observed data by asking lots of questions, counting the number correct, and then adjusting for age. And this results in the estimate of the IQ, the latent variable. In economics, the maximum amount that people are willing to pay for goods would be the latent variable. It's the inferred from the transactions, which would be the observed data using a random effects model. The simplest approach to measuring a latent variable is to find a single observed variable that's believed to be sufficiently accurate measurement of the latent variable. If you want to ask people how much they'll pay, you can ask directly. Or if you want to gauge intelligence, you can present people with a difficult mathematical equation. But either way, this is like a single observation that we're doing. And then the composite variable is two or more variables combined to make a more complex variable. So overall health is an example of composite variable. If you use other variables such as weight, blood pressure, chronic pain, all of this to determine the overall health in your experiment. So for scales of measurement, nominal scale, this is used for qualitative data. It doesn't give any numerical meaning to the data. It can be classified. It can't be subtracted, multiplied, divided, added. Some of the situations where nominal measurement scale can be used would be like a study to find the country of birth people in a small town, collecting data on the eye color of people, classifying people into categories like male, female, working class, population, unemployed, vaccinated, unvaccinated. Some of the properties of the nominal scale. It can categorize variables, but it doesn't put them in order. It does not show any numerical value. It's used for qualitative data. But the ordinal one, that is the one that we use to rank. And so it contains the property of nominal scale as well, which is to classify data variables into specific labels. But in addition to that, it can organize the data into groups, though it does not have to have any numerical value. For example, the study of people's satisfaction with the company's product on a scale of like 1 to 5, where 1 is very happy, 2 is satisfactory, 3 is neutral, 4 is unhappy, 5 is extremely dissatisfied. This is an ordinal scale of measurement. We can also use this measurement scale to rank players in a race, look at things from hottest to coldest, richest to poorest, people's satisfaction with products, other people, government. The properties are, it displays the order or rating. It does not give numerical value to the data, so it's also used for qualitative. And it contains variables that can be placed in order like heaviest to lightest, ranks of players or students, etc. The interval scale of measurement includes values that can be measured in a specific interval, like time, temperature. It shows the order of variables with a meaning, proportion, or difference between them. Like a temperature scale, the difference between 20 degrees Celsius and 30 degrees Celsius is the same as the difference between 50 degrees Celsius and 60 degrees Celsius. This is an interval measurement scale. On the other hand, though, the difference between the scores of the first 2 rankers in a race and the 2 runner-ups will be different, right? So that's an example of an ordinal scale. Some of the properties of an interval scale would be, it includes both nominal and ordinal scales. It shows meaningful divisions between variables. The variables can be presented in numerical terms. They can be added or subtracted from each other, the variables can. It also gives meaning to 0, which is not possible in the above 2 scales that I talked about. For example, 0 degrees of temperature. The ratio scale of measurement, this is the most comprehensive one. It includes all the properties from all of the other 3 scales of measurement. It has a unique feature of the ratio scale of measurement. It considers the absolute value of 0, which was not in the case of the interval scale. When we look at the height of the people, 0 inches or 0 centimeters, that means the person does not exist. On the interval scale, there's values possible on both sides of 0. For example, temperature could be negative as well. While the ratio scale does not include negative numbers because of its feature showing absolute 0, an example of the ratio measurement scale is determining the weight of people from the following options, like less than 20 kilograms, 20 to 40 kilograms, 40 to 60, 60 to 80, more than 80, and so forth. So properties would be it's used for quantitative data. It shows the absolute value of 0. We can add, subtract, multiply, or divide. We can calculate the mean, the median, the mode. It doesn't include the negative numbers because of the true value of 0, but it is the most comprehensive of these 4 scales of measurement. All right, so we know reliability is important in research, right? For test retest, we want to measure the consistency of results when we repeat the same test on the same sample at a different point in time. We want to see that constant or that consistency in your sample. If we're going to test color blindness for a trainee pilot, that should have high test retest reliability because color blindness is a trait that doesn't change over time. But there are factors that can influence results at different points in time for some tests. So, respondents might experience different moods or external conditions, and that might affect their ability to respond accurately. In order to test retest to use test retest reliability, we want to be able to assess how well a method resists these factors over time. The smaller the difference between the 2 sets of results, the higher the test retest reliability we get. The internal consistency assesses the correlation between multiple items in a test that are intended to measure the same construct. You can calculate internal consistency without repeating the test or involving other researchers, so it's a good way of assessing reliability when you have only one data set. When you devise a set of questions or ratings that'll be combined into the overall score, you have to make sure that all of the items really do reflect the same thing. If responses to different items contradict one another, then the test might be considered unreliable. And for the inter-rater reliability, this measures the degree of agreement between different people observing or assessing the same thing. You would use this when data is collected by researchers, assigning ratings, scores, or categories to one or more variables. Like in an observational study where a team of researchers collect data on classroom behavior, inter-rater reliability is important. All the researchers should agree on how to categorize or rate different types of behavior. People are subjective, so different observers' perceptions of situations and phenomena naturally differ. Reliable research aims to minimize subjectivity as much as possible so that a different researcher could replicate the same results. Just like reliability, validity is also very important when it comes to research. So with face validity, does the content of the test appear to be suitable to its aims? And we want to know how suitable the content of a test seems to be on the surface, right? So it's similar to what we'll talk about with content validity, but face validity is more informal and subjective assessment. You create a survey to measure the regularity of people's dietary habits. You review the survey items, which asks questions about every meal of the day, snacks eaten, every day of the week. On the surface, this survey seems like a good representation of what you want to test, so you consider it to have high face validity. Face validity, though, is a subjective measure. It's often considered the weakest form of validity. However, it can be useful in the initial stages of developing a method. Construct validity evaluates whether a measurement tool really represents the thing we're interested in measuring. It's central to establishing the overall validity of a method. It refers to a concept or characteristic that can't be directly observed, but it can be measured by observing other indicators that are associated with it. Constructs can be characteristics of individuals such as intelligence, obesity, job satisfaction, or depression. They can also be broader concepts applied to organizations or social groups, such as gender equality, corporate social responsibility, freedom of speech. There's no objective, observable entity called depression that we can measure directly, right? But based on existing psychological research and theory, we can measure depression based on a collection of symptoms and indicators such as low self-confidence and low energy levels. So we want to, with construct validity, it's about ensuring the method of measurement matches the construct you want to measure. If you develop a questionnaire to diagnose depression, you need to know, does the questionnaire really measure the construct of depression, or is it actually measuring the respondent's mood, self-esteem, or some other construct? In order to achieve construct validity, you have to ensure that your indicators and measurements are carefully developed based on the relevant existing knowledge. The questionnaire must include only relevant questions that measure known indicators of depression. And then the last one here, the criterion related validity, evaluates how well a test can predict a concrete outcome, or how well the result of your test approximate the results of another test. So the criterion validity is an established and effective measurement that's widely considered valid. Sometimes it's also considered like the gold standard measurement. Criterion variables can be very difficult to find. To evaluate this criterion validity, you calculate the correlation between the results of your measurement and the results of the criterion measurement. If there's a high correlation, it gives a good indication that your test is measuring what it intends to measure. For example, a university professor creates a new test to measure applicants' English writing ability. To assess how well the test really does measure students' writing ability, she finds an existing test that's considered a valid measurement of English writing ability and compares the results when the same group of students take both tests. If the outcomes are similar, the new test has high criterion validity. So participant reactivity can affect how well your experiment is going to be understood and what data you receive. In some cases, it can help the researcher in giving a wider range of data. However, they normally can be or are a hindrance. There's a variety of different types of reactivity that can be recorded and controlled, including what's known as the Hawthorne effect, which is a set of changes that people subconsciously make when they know they're being watched. This can be something such as pressing a button slower than normal, as they're concentrating too hard, or they're nervous about some part of the experiment. We can account for these effects by making sure we use the correct research method design for the experiment and by using a wide enough range of samples. As well as this, participants can become bored and unwilling to participate further without withdrawing the information. Some participant effects, such as experiment bias, are hard to account for, as they may be present in all of the participants tested. Experimenters can impact how the participants behave and react throughout their manner and their instructions that they provide to participants. For instance, if an experimenter comes across as rude and aggressive, then the participant is more likely to be intimidated. Right? In Milgram's famous learning study, he conducted the study with both friendly and unfriendly researchers and found that compliance is more likely when the researcher is harsh and unfriendly, as we perceive them as stronger and dominant. Demand characteristics also have an impact on our research or on our data and should be avoided at all costs. Out of all the different impacting forces on our data, demand characteristics are the easiest to control, as it requires being careful not to include participants who have already completed our task beforehand. All of these problems can account for outliers in the data. This is why it's important to understand and be able to recognize them. If we can recognize them, that they may be the reason for data behaving oddly, then we can adjust our stats and allow for more accuracy when rejecting or accepting the hypothesis.